So let's start with a little bit of terminology. In Greek, poly means many. These are examples of polynomials. Now in Greek, mono means one, bi means two, and tri means three. So as you see from the examples, monomials are specific case of polynomials where there is just one term. A binomial is a polynomial with two terms, and a trinomial is, surprise, surprise, a polynomial of three terms. Okay. Today we're going to focus on binomials. The binomial theorem is addressing the fact that once we start multiplying binomials, even the ones by itself, things get sort of out of hand. In my eyes, this is a case of all the trouble that the distributive law causes. This is when multiplication and addition are meeting, and things are not pretty. These are the first 6 powers of the binomial a plus b. You probably know how we compute those. A plus b squared is a plus b times a plus b, and then we apply the distributive law, and then we combine like terms. For the next one, for a plus b to the third power, we're just going to grab the previous one and multiply it by an additional a plus b. The issue is that these expressions don't stay short. They get longer and longer and more cumbersome. Difficult. So a times these three, and then b times those three. So we can expect 6 little pieces of products. There is a trick here, is instead of going straight, sort of to push enter and tab. And this is what we get when we multiply all these three terms by b. And if you were arranging them so cleverly, then the like terms are actually organized by columns. So a plus b to the third power is a cubed plus 3a squared b plus 3ab squared plus b cubed. And this one is 4 terms long. So when we multiply it by an additional a plus b, we can expect 8 little pieces of products. And then when we combine like terms, chances are it's going to be 5 long. Well, here are the first few worked out. So a plus b to the fourth power has 1, 2, 3, 4, 5 terms. As a matter of fact, it looks like you just need to add 1 to the degree, right? Binomial has 2 terms. If you raise it to the second power, it will have 3 terms. If you raise it to the third power, it will have 4 terms, and so on. And that is not so strange, because in a plus b to the fourth power, we are counting to 4 only we include 0. So that 5 is going to be, if you look at this line, how many a's are in this expression? This one has 4, 3, 2, 1, none. So a plus b to the fourth power will have 5 terms. The binomial theorem is trying to address this mess. We do not want to spend 2 pages just to figure out what a plus b to the 10th power looks like. Alright, let's get started. So the question is there a mathematically justified shortcut through all these computations? Suppose I'm only interested in a plus b to the 7th power. Do I really have to compute all the previous cases? Is there another way to get to a plus b to the 7th power? And the answer is yes, and that is what the binomial theorem explains. Suppose I would like to expand a plus b to the 7th power without computing, say, a plus b to the 6th power. If we are trying to generate or recall a polynomial, basically we're dealing with the coefficients and the variables. The variables, that's going to be easy to predict. If we look at, for example, a plus b to the fourth power. Here we're multiplying 4 a's. And then imagine we step to the right and we throw away an a and pick up a b. So now we have 3 a's and a b. And then repeat. Throw away an a, pick up a b. Now we have a squared b squared. Again, throw away an a, pick up a b. Now we have just 1 a left and 3 b's. And finally, when we get rid of our last a, they become all b. And that is the same to say that we are counting from 0 to 4. So if we had to write a plus b to the 7th power, then we could probably guess the terms, right? It will be probably 8 terms, the first one being a to the 7th. And then the second one we will obtain by throwing away an a and picking up a b. So that's a to the 6b. And then repeat a to the 5b squared. See, we're decreasing the number, the exponent of a's, and increasing the exponent of b's. A for b3. And it's easy to check. Each term has to be of degree 7, so you can just add the exponents to see if we're still in the right track. So we can predict the terms being from a to the 7th, then we throw away an a, pick up a b, and we continue doing that until they're all b's. So these are 8 terms, depending on how many organized by, say, how many a's are there, from 7 to none. And this is a long expression. I couldn't even fit it on one line, so it would be helpful if we could do this without multiplicating up to it. So the signs are easy in this case, right? They're all going to be plus. But what about the coefficients? That is the challenging part. If we go back and look at the coefficients of these terms, they get more and more complicated. The last thing that's left for us to do is figure out the coefficient, and that's where it gets interesting. We can get a plus b to the 3rd power by multiplying a plus b by a plus b, and when we're done, we further multiply by a plus b. But that is not the only possible way. We're going to work out a plus b to the 3rd power in a little bit of a different fashion. Another way of multiplying here is the following. We're going to go into the first parenthesis and select either a or b. Then we're going to go into the second parenthesis and select either a or b. And then we're going to go into the third parenthesis and select something a or b. We have one variable from each of these factors. Then when we multiply them together, we get a little degree 3 product. Our alternative method will work fine as long as we can do this in every possible way. If we go into the first parenthesis, we have 2 options. If we go into the second parenthesis, we have 2 options. Same here. So altogether, we have 2 times 2 times 2, 8 options, which means that, so we should expect 8 little products. Let's just list them first. So suppose we pick a from the first one, a from the second one, and a from the third one. That will give us the little product a cubed, right? So now we're going to get a little bit systematic and fix the beginning as much as we can. So how about a from the first, a from the second, and from the third one, we pick b. So then the little product that we get is a squared b. So the next one is a from the first parenthesis, b from the second, a from the third. So that's also a squared b. What's next? A, b, and b, right? So that would be ab squared. We're halfway through. We can just repeat this and change a to b, and that's going to be the other ones. And these are all the possibilities. So when we multiply these little products out, ab squared, and now we combine like terms. We have 1a cubed. As for a squared b, we have 1 here, 1 here, 1 here. 3a squared b. As for ab squared, also 3. We have only 1 b cubed. And if we compare that with our previous result, we see that we have the same result. A cubed, 3a squared b, 3ab squared, b cubed. Same here, a cubed, 3a squared b, 3ab squared, b cubed. Don't ever feel that systematic listing is silly or you're beyond that. Many times, that's how we get the idea. And this might be a little bit specific to combinatorics, but I often find that as I perform systematic listing using the smaller cases, I actually change notation or my method of counting. And So what we're going to do next is we're going to work out the next one, a plus b to the fourth power, but we're going to make a few changes. So one of the changes I'd like to make is to organize it by terms. Say we want to find how many different ways can we get a to the fourth. Sorry, that's my cat. So how many different ways can we get a to the fourth power? Well, for that there is not that many choices. In all four parentheses we have to choose a, so there is just one way. But it's going to get a little bit interesting. How many different ways can we get a cubed b? Well, that means that in 3 places I pick a, at one place I pick b. That can happen in 4 different ways because there are 4 different ways to pick one factor to select b from. If you notice, this is getting less readable if we write down both a and b. Our other improvement could be, let's just write down b, and then whatever is empty, that's automatically accepted to be a. We have 4 different little products that yield for the same term a cubed b. Okay, the next one a squared b squared. B could be either in the first and the second, or the first and the third, or the first and the fourth. We kind of discover the contours of our next notation. 1 and 2 are the spots where we pick b. 1 and 3 are the spots where we pick b. And then 1 and 4. What could be next? We ran out of cases that start with 1, so let's roll up to 2. 2, 3, 2, 4, 3, 4, and that's pretty much it. So how many little products did we get? 6 of them. 6. A squared, b squared. Well, the bulk of the work is done because you should probably have an instinct about symmetries here. So far we had an a to the fourth, 4a cubed b, and we just finished counting 6 of the a squared b squareds. The next thing that we want to find is ab cubed. Well, that means that in 3 parentheses we are selecting b, and in just 1 parenthesis we select a. Now it's easier to follow the a's, and there are exactly 4 ways. And that is not surprising. There is this outer symmetry. A cubed b should be very similar to ab cubed, given that the whole problem is symmetrical in the end. We're only going to get 1b to the fourth power. If we went into each parenthesis and had a choice of 2, altogether that's 2 to the fourth power, that's 16 choices. Do we have the 16? 1, 11, 16, yes. Now we know that this is a plus b to the fourth power, and if we go back to our original and compare, we see that we got it right. Okay, you're right. Your suspicion is correct. We're gonna start figuring out what a plus b to the fifth power is, in case you didn't have enough listing. Let's figure out what a plus b to the fifth power should be. What kind of terms can we get? We have 5 parentheses. In each of them, we have a choice of 2, which means we should expect 32 little products. A to the fifth, but that is just a. And then the next one, a to the fourth, b, and the next one is going to be a cubed b squared, and then a squared b cubed, a b to the fourth, and b to the fifth. So we have these 6 types of products. A to the fifth power, there is just 1, right? What about a to the fourth b? In one factor we pick b, and all the others we pick a. Then basically the question, which parenthesis did you pick b? Well, either the first or the second or the third, and so on. So there are 5 of those. Okay, let's see the next one. So a cubed b squared. So that means that we're going to write 2 b's. We're going to leave the spots for a empty, and we have to do it in every possible ways. This would be equivalent to 1, 2, right? The first and the second. And then there is 1, 3. 1, 4, 2, 2 and 3, 2 and 4. Okay, that's my other cat, baby. So next up, we are the 2, 3, 2, 4, 2, 5. Here's the question, what are we counting here? What are we really counting? So the next one is 3, 4, and then 3, 5, and then 4, 5. So how many? These are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 many. So we're going to have 10 So we're going to have 10 a cubed b squared, and by symmetry that means we're also going to have 10 a squared b cubed. By symmetry we can expect 5 for a b4 and just 1 for b to the 4th, and that should add up to 32. Did we get them all? 20, 30, 32. Okay, so the big question is, what did we count here? So in the case of a cubed b squared, we just traced where b could be selected, and out of 5 parentheses, twice we had to pick b, and that's 5 choose 2, right? Out of the 5 spots, which 2 did we select to select b from that? And the rest was by default a. So that, as you know, is 10. So there is a deep combinatorial connection here with combinations and the binomial theorem. So let's just figure out, given what we have found, what a plus b to the 7th power should be. The terms, obviously this is not going to fit. There is going to be a to the 7th, and then a to the 6th b, and then a to the 5 b squared, a to the 4 b cubed, and then a cubed, b to the 4 a squared, b to the 5 a b to the 6, and b to the 7th. So we know that this coefficient is going to be a 1. But that's the same thing as 7 choose 0, right? We're tracing b's right now. How many b's are we going to select? None, because all of them is going to be a. So, and we all know that the value of this is 1. We have 7 factors, all of them a plus b, and 6 times we are going to select a, and 1 time we are going to select b. That's 7 choose 1 many possibilities, which is 7. A to the 5th power b squared means that in every possible ways we have to pick 2 factors to select b from, the rest will be a. That means that out of the 7 spots we choose 2. So that's 7 choose 2, which is 21. Next up, 7 choose 3. So that's 35. And then by symmetry we can expect again 35, again 21, again 7, and again 1. Picking 6 for b is the same as picking the 1 for a. We are not married to tracing b. We can swap to trace the one that's more convenient. This outer symmetry which we have seen is that n choose k is the same as n choose n minus k. Right? To select 6 out of 7 is the same as selecting the one not selected. So this would be 7 choose 4. That 7 choose 4 is the same as 7 choose 3. And then 7 choose 5 should be the same as 7 choose 2. And 7 choose 6 is the same as 7 choose 1 or 7. So there it is. A plus b to the 7th power is a to the 7th plus 7 a6b plus 21 a to the 5b squared plus 35 a to the 4b cubed plus 35 a cubed b fourth, 21 a squared b to the 5, 7ab to the 6th power, and 1b to the 7th power. That's it. You don't even have to state the binomial theorem, you just have to apply it correctly. But let's just state it just for the fun of it. We're going to state it twice. A plus b to the nth power. The first term should be a to the nth power, right? The second piece should be a to the n minus 1b, and how many? That coefficient should be n choose 1. Then, next, we throw away an a, pick up a b. What should be the coefficient? Well, out of the n spots, we need to pick 2 for b, then the rest is automatically a. So that's n choose 2 many ways. The next one is a to the n minus 3b cubed, and surprise, surprise, n choose 3 many ways. Can we select the 3 parentheses to select b from? The rest is automatically a. And so on. We can interpret this as n choose 0. Same thing as 1. Basically, this number copies the exponent of b, and we're going to go from 0 till n. So the one before the last would be when we're almost out of a, almost all of it is b, and the last piece, n choose n, is just b to the nth power. So this is the binomial theorem stated in its full generality. Let's just state it again as an exercise, but this time with sigma notation, summation notation. So n is fixed. But that our variable, the counting variable, should be this one. It changes, and this is the one where we traced b. So these numbers should be always the same as the exponent on b. So if we make k to be that number, then k ranges from 0 to n there. Well, this is the easiest part, right? We have k many terms of b. This is n. This is n minus 1. This is n minus 2. If you notice, if we add the 2, we should always get n, because these are still n degree product. And now for the coefficient, it doesn't matter which one we write. It can, what we have done is basically n choose k. So that is the binomial theorem. Thank you for watching.